If you use a power law distribution, you will need to specify at a minimum a lower cutoff size, because you can imagine this curve just keeps going up and up and up, and you could end up with zillions of tiny fractures. So you definitely want to specify a minimum size, and often you will also specify a maximum size. Maximum size is necessary, especially if you're making 3DEC models, because you don't want to generate thousands of tiny fractures that have very little effect on the mechanical behavior of the system. Okay, so here's how it works. You figure out the disk diameter from some size distribution. It could be a power law. It doesn't have to be. So if you plot it on non-log scale, you would see with more small fractures and less big fractures, and you usually specify some minimum. Next, you figure out the orientation sampled from some distribution. Often you will see an orientation distribution defined by a stereo net. So I assume that you're probably familiar with these types of plots. And again, you might need to do some sort of bias correction to figure out the orientation. Once you have a size and an orientation, you just plop it into the volume, usually in some random location. This plot here is showing you 2D just to make it clearer. So you keep on adding fractures into the system until you reach some specified threshold for density. The density could be, again, P10, which is the number of fractures per unit length along some line, or it could be P21, which is the length of fracture per unit area on some surface. So you just keep on going. And then what you probably do is check. So maybe you have one borehole defining when to stop, and maybe you have other boreholes that you're using for checking. You check the fracture frequency, and maybe it's not correct. You can change the size distribution depending on which way you were wrong. Because again, often you have a good idea about what the orientation distribution is, a less good idea about what the size distribution is. So this is probably the parameter you're changing to try and get a better match. Okay, other things to consider. You can create a DFN completely outside of 3DEC model. So you can just create a whole bunch of disks and look at them. But we assume that probably you are wanting to create an actual 3DEC model out of this thing. What you should be careful of is that when you create the fracture network, it again randomly tries to put these disks into a box. If the centroid lies inside the box, it creates it. And if the centroid lies outside of the box, it doesn't create it. What this means is that there's probably a bunch of fractures that lie outside of the box that don't get created. But in reality, part of that fracture would be poking inside the box. So what it means is that around the edges of the box, you have a density that is not high enough. Because you're missing all of these fractures that are lying maybe just outside of the box. So what you should do is generate the DFN system in a volume bigger than you intend to use. So if you're making a 10 by 10 by 10 meter 3DEC block and cutting it up, you probably want to generate DFNs in maybe a 20 by 20 by 20 meter block to account for this effect. The other thing, if you're planning on making a 3DEC model out of this, is that if you have fractures that are very close together and almost parallel, this will be a big problem because you will end up with long, skinny blocks. They're difficult to zone. They'll mess up your time step. There are potentially other problems if you're running a large strain. So you include this command fracture merge, and this will allow you to merge together fractures if they're close together and subparallel. And you probably want to do this if you're making a 3DEC model. So let's pretend you've created your discrete fracture network. It's all disks. Note it doesn't have to be disks. If you import from some other program, especially say FracMan, they could come in as polygons rather than disks. But if you use the generation function that's built into 3DEC, they come in as disks. Now you want to create a 3DEC model out of this. Here's how it works. Now recall from previous sessions that you cannot cut partway through a block. You only can cut all the way through a block. So we can't just cut out little discs from a block like this. What you have to do is use these discs to cut all the way through the block, but we can do this in an intelligent way. And so what we do is we sort from largest to smallest, and we start with the largest. So imagine this one here closest to the screen is the largest. We cut that one first. We have no choice. We have to cut all the way through the block, and this is what it looks like. The second biggest one is perhaps this one, trending north-south. Now we make that cut, and again, we have to cut all the way through the block. Now we get to the third fracture. This is the smallest. It has to cut through all of the blocks that it's in contact with, but it doesn't have to cut through all of the blocks in the whole model. So in this case, we only need to cut this light blue block. It doesn't actually extend into the brown one, it doesn't extend into the red one, and it doesn't extend in the green one. So here we only need to cut the light blue one. So you can imagine if you had many, many fractures and you sort from large to small, this gets more and more efficient as you go along. You're cutting fewer and fewer blocks. Don't end up having to make a whole bunch of cuts that are unnecessary. But now you've still got a problem. You've got joints in here that are bigger than the actual joints of the DFN. So what do you do? To account for that, you assign different properties to the subcontacts inside of the fracture and the subcontacts outside of the fracture. And there are built-in commands to make that relatively easy. So you can say, assign some properties, whatever they are, cohesion and friction, and you say range DFN 3DEC, and you give the name of the DFN, and it will assign those properties to all of the subcontacts that lie inside of the disks. And it will not assign those properties to the subcontacts that lie outside of the disks. And so in this way, you could, for example, have a low friction and a zero cohesion in here, where there's a true fracture, and a higher cohesion and a higher friction outside of that region, where it's really not a true fracture. Or maybe you want this fracture to propagate, so you give it some higher cohesion and friction that maybe it will propagate out here. Or maybe you don't want it to propagate and you essentially make an infinite cohesion and friction. Or you could even make it elastic. It's possible to specify different constitutive models inside and outside of these disks. So over here on the right, you can see the same model we just showed in the previous slide with 3 intersecting disks. And what happens is by messing around with the properties, you can see these red circles show you where the disks actually are, and maybe you have a realistic cohesion and friction, and the rest of this is assumed to be elastic or something like that. So that's basically it. This will hopefully become a little more obvious by doing a small tutorial and showing you how this works actually in 3DEC. So escape out of PowerPoint. We'll start 3DEC. Now I've given you a project here. So let's say open existing project. If you find where the documents are that you downloaded for this training course, training, 3DEC training. There's a directory called DFN, so go in there. There's a DFN tutorial. And again, there's a solution directory, because when we do this live, we have the students follow along and type things and start from scratch. Just to save time here, we can actually open the existing solution. So go into that directory, open the project. Okay, you can see what we're doing here. So model new, as usual, model random 10,000. If you haven't done this before, this is setting a random seed such that every time I run this model, I will get exactly the same result. With discrete fracture networks, this is especially important because there is inherently some randomness to the DFN. You give a distribution, but then it just puts the fractures in randomly. So you can potentially get a different manifestation of this DFN every time you run the model. And maybe you want to do that. Often you might want to run 10 or 100 different models with different random DFNs. Fantastic. You could either leave this line out, and every time it says model new, it will just come up with a different random number. Or you can intentionally change this to be something different each time, 10,001, 10,002, 10,003, whatever you want to do. By specifying this, if I run this over and over again, I get the same answer each time. Creating these DFNs, you need to give a domain. So remember I said that you create a box and you fill that box with fractures. There has to be some limits to that box. We just can't have fractures going out infinitely into space. So you give some domain extent, in this case, -50 to 50, and it assumes that y and z are the same. So it goes from -50 to 50 in the x direction, the y direction, and the z direction. So we've got 100 by 100 by 100 meter block. Now, the way that these DFNs are created is first you create a template, and this is where you define the distribution of orientations, the distribution of sizes, and so on. With this single template, you could create multiple DFNs. So the template just gives you the definition of the distribution. When you actually generate the DFN, then it creates the fractures. And again, they can be different depending on the random seed and so on. So first we need the template. We give it a name so we can refer to it later. We give the size distribution. In this case, we say power law. I said in the previous slide that the power law in 3D is usually around 4, that exponent that defines the slope of the line. For this example, we use 3. If you use 4, it's fine, but you just end up with a lot more small fractures. And our plan is to make a 3DEC model down below here. So just to prevent the formation of many, many small fractures, we're going to use 3 in this case. And again, you probably want to give some size limits. So in this case, the minimum is 2, the maximum is 20. The size limits, this is diameter. So that it'll create discs. The minimum size disc will have a diameter of 2 meters, and the maximum size disc will have a diameter of 20 meters. It's going to position them uniformly, and the orientation is going to be uniform. This is the default. I don't actually need to type this in here, but it's not a bad idea just to remind myself later that I intentionally made a uniform distribution here. So this is the template. There's a separate command to actually generate the fractures, and it's fracture generate DFN. You have to tell it which you have to give it a name for the DFN. You don't have to, but we will use this later when we create the 3DEC model. And again, it's possible to create multiple DFNs within one model. In this case, we're just making one. So we give it a name, my DFN. We tell it which template to use, DFN template, which we just created. And then you need to tell it some sort of measure of density. In this case, we're using this academic mass density, which was this P32, the area of fracture per unit volume. Recognizing that this is not really something that you can measure in reality. In reality, you might use something like a different measure of density related to the number of fractures per meter on a borehole or something like that. And we can show an example of that in a minute. So for now, we'll just use this mass density, and it creates the DFN. So we can just run these lines. Already done it. 7,338 fractures. I've given you a plot here with DFN, but just to show you how it's done, we'll create a new plot. So I go new plot. I'll just call it DFN2. Go to the plus to add fracture. Let's hide this view shift. Okay, so here's all the fractures that I just created. You can see they're mostly discs unless they are intersecting the boundary in which it truncates them. By default, they come in all the same color, but you can choose different things to color by here. So under numeric value, for example, I could choose diameter. And now it makes it clear where the big ones are and where the small ones are. There are other things you can do here. When I have these fractures, I could also plot a stereo net, which gives you some indication about the orientations. So if I go up here and I go plus under fracture, there's fracture stereo net. In this case, it's not very interesting because we told it to use a uniform distribution. But anyway, here it is, and you can actually plot the points on here. These are the normals to the fracture orientations. And again, they're fairly randomly distributed, as you would expect. Just for fun, we can try and make something that's less randomly distributed. In 3D, people often use what's called a Fisher distribution. So I can say orientation instead of uniform. I can say Fisher, and then I have to give a dip. So I don't know, 30 degrees, a dip direction, 210 degrees. And then I give a kappa parameter, which is some measure of randomness. And actually the bigger the number, the tighter the cluster of fractures that are created. So let's put in 500. You can read about this on Wikipedia or whatever. Let's just try this. So we'll run this again. Now let's go back to our plot. Wow, okay, that is pretty tight. But you get the idea here. This is the normals to the joints. So the joints are off here dipping, what did we say? 210, the dip direction, and 30 is the dip. So they're dipping off here somewhere, and this is the normal to those planes. I turn off the points, you can see that. Let's give it a little bit less randomness than that. Let's make it, say, 200. See what it looks like. Sorry, a little bit more randomness, I should say. That didn't make a huge difference, but you can play around with these parameters and get different orientation distributions. Okay, for this example, let's put it back to uniform. Last thing related to the DFN is that we want to find fractures that are close together in space, so within a distance of 0.1 meters, that are subparallel, so within an angle of 5 degrees, and we're going to merge them together. And this way, we don't have very close together subparallel fractures when it comes time to create our 3DEC model. So this is a useful command, and what it does is if it finds two fractures that are close together and subparallel, it just merges them into one fracture. So I can run all of this. At the end, I'm just going to save it. Okay. So there's my original DFN. Here's the fractures. So now I want to actually create a 3DEC model. We've talked about this before. Sometimes you want to reduce the tolerance from the default to make sure that you actually cut all these fractures. In this particular case, even with reducing the tolerance, some of them will still not cut. This is the minimum block size that it will create, 0.02 meters. By putting in these fractures, it still tries to create blocks smaller than that and rejects the cut sometimes. I create one brick, minus 10 by 10. Notice that this brick is quite a lot smaller than the domain in which I built the DFN, because of the thing I talked about before, where you have to account for the fact that there might be fractures outside of the domain poking in. I want to make my brick smaller than the extent of the DFN. So I make it minus 10 to 10, and then I just cut it. And it's super easy because the command's right here, block cut DFN, name, and I just give the name of the DFN that I created up here. So we can just run that part. Oh, actually it did not reject any fractures, so that worked fine. Now I can go and look at blocks. Okay. So remember how it works. It sorts from the largest to the smallest, and it has to cut all the way through the blocks. So what you see is a bunch of cuts here. And again, most of these joints are bigger than you actually want. But we have cut in all of the discs into this model. So what we want to do next is to assign different properties to the subcontacts that exist inside of the disks and those that exist outside of the disks. We haven't actually got any subcontacts yet. Subcontacts are created when we do the zoning. So the first thing we need to do is the zoning. And for this model, we'll just make the zoning the same everywhere. It tries to generate and tests with an edge length of 1. In a lot of cases, that will be smaller than that because of the way the cuts are. It just basically fills up the volumes with zones. And this is essentially a maximum edge length. A lot of them will be smaller than that. You can go back and look at our blocks and see the zoning. That all looks good. Now, you would go now and set all of your properties for the joints. Well, first you could probably set your properties for the zones. We're going to skip that step. Then you would set the properties for the joints. And again, normal stiffness and shear stiffness and so on. We'll skip all of that. For the purpose of this tutorial, we're only going to look at friction and cohesion. So imagine you have a friction of 30 degrees and a cohesion of 1,000 for all of the joints outside of the fractures. But on the fractures themselves, we say the cohesion is 0. So we're assuming that there's only frictional resistance to sliding for these fractures. Outside of the fractures, there's some cohesion that needs to be overcome. So you can imagine in this situation, if we actually loaded it under some stress, the guys that are inside the discs could potentially start sliding, depending on the normal force. But there will be extra resistance to sliding outside of the discs because of this cohesion, which could be overcome, and you could get some sort of propagation. If you did not want propagation, you could make this a really, really high number. So line 34 will set properties for all of the subcontacts, 26,000. And now it's going to assign properties just to the ones inside of the discs. And you can use this range DFN 3DEC, my DFN. Again, you give the name of the DFN, and it will find all the subcontacts that lie on the discs and give them different properties. So if I want, you can see that it assigned a cohesion to 3,102 subcontacts. If I want to convince myself that this actually worked, I can go here and plot the joints. So I've given you a joint plot, but I'll just show you how to do it from scratch. I'll make a new plot. I'll call it joints 2. I go to plus. I have a joint plane. So here's all my joints. Let's change this color by to contour. And let's change the contour to property. It defaults to cohesion. So what you can see here is that all of the red areas have a cohesion of 1,000, and all the blue areas have a cohesion of 0. And so the you can see where the discs are, where these blue areas are correspond to discs and DFN. I can plot the discs on top of this here to convince you that it's correct, but remember that the volume of discs is humongous, so it's going to obscure this thing. But we can do it anyway and just change it with a range. So let's add the discs to this plot. Fractures. Right, so here there's the 100 by 100 by 100 meter block full of discs, so I can't actually see what's going on here. Let's reset this back to the XZ plane and zoom out. Now I can make a clip box to hide all of these fractures outside of the block. So under my fracture here, if I expand it under cutting tool, oh no, below that is clip box. So if I turn on the clip box, right, it gives me a little box here and hides everything outside of that box. I can make this box a little bit bigger, sort of just bigger than the 3DEC block, third dimension here, just by grabbing these things and moving them. In fact, I can even move the centroid of that a little bit, move it to the middle of the block, and then reduce the size. There, okay, we're done with that. Let's zoom in. Hopefully now you can convince yourself that where the discs are is where the subcontacts have been given 0 cohesion. See this one here at the top, this one here. this one here, this one here. And so you can see that the logic worked. You might, to make a nice plot or a nicer plot, want to hide all of the sections of the joint that are not part of the DFN. And so you could do that with a plotting range. So if I click on my joint plane plot item, I expand it and I go to range, and I right click on that and say add range element. One of the range elements I can choose is DFN distance. So if I choose DFN distance, it shows you a list of the DFNs in here. I've only got one, so I choose my DFN. By default, it's plotting not everything that's within a distance of 0 of that DFN. I actually want to plot the things that are within a distance 0 of that DFN, so I check the not box. And 0 is a little bit severe because there is some, tolerance in here. So let's make it a slightly bigger number than 0, say 0.1. Okay, how about 0.01? Let's see what happens then. Okay, now I can turn off my fractures, and I can see just the parts of the joints that are within a distance of 0.01 of an actual disk. If I turn this contour back to label, I got a slightly nicer plot here showing me. That's a bit jaggedy, right? Because it can only do it triangle by triangle. You're not going to get a perfect match to those disks, but you get the idea. And depending on how high resolution you do with your zoning, you can get a better or worse match to those disk boundaries. Okay, that's basically it for this example. The last thing might be to investigate what the actual joint density is along some line, because in reality, you probably have some sort of borehole. So there are commands related to printing out fracture information. I'm going to try to remember here off the top of my head. Fracture, I can't remember, so I'm going to hit Control Space. It's probably like fracture print or fracture list. Fracture list. That's not it. Fracture information, maybe. I have to pause this video while I figure this out.